So I'd like to do a Python Scikit demonstration, and then following that, a TensorFlow keras demonstration. In this example, I want to learn a little bit of Python, maybe explore importing a CSV, and also using Scikit. So the way we're going to do this is we're going to create a fake data set of gulls, a type of bird, with the intention that we're going to have a couple attributes of the birds, and we're going to run machine learning algorithms on them and then use it to predict other types of birds within our generated data set. These are the main packages that we're going to use. Actually, we don't need requests. But so this is for plotting. What you do is you type in import matplotlib.pyplot as plt, and then from there you can plot using plt.plot, and then you give it some like x variables like 1 and 2, then you give it some y variables like 3 and 4. Then when you do plt.show, it'll make a little line and stuff like that. So this is how you plot stuff. Then NumPy is essentially how you do matrix and vector analysis, and also advanced random variables. It's like you can do np list 1 2 3 4, and I'm just going to give it the letter A, print A. So np array, so it's just an array here, and you can transpose it like this. So @ symbol is the cross multiplication, and there you go. Now you have a matrix multiplication. So to break the syntax down just for a moment, you see that you have np array, and then what you pass into it is an object. In this case, I gave it a list of lists just to make it a matrix. If I just give it a list, it doesn't seem to work. So by doing this, I'm saying it's a one row. It's a here we can do a.shape. So it's a 1 row 4 column vector, and then when you do a.transpose, now you get a 4 by 1 vector. So print A, and then A transpose. So this is A, and this is A. This is A. This is A transpose. Yeah. So anyways, that's NumPy lets you do a bunch of vector analysis stuff, and then pandas is a data frame. If you're not familiar with data frames, it comes from R, and it's essentially the idea of like using an Excel spreadsheet, using two-dimensional data with columns, and doing whole row operations and stuff. Then this is just the native Python library that lets you just generate some random variables. So we're gonna just talk about some gulls. We're gonna give them attributes. I'm sure you've all seen seagulls at some point in your life. This is just a herring. This is the snowy American herring, and then this is just another one. Yeah, they have some variety to them. Visually, there's a bunch of different types of gulls, and in this example, we're going to give them the attribute of boldness, intelligence, timidness, and wealth. Okay, and so this is kind of just an arbitrary thing. I'm just setting up an experiment where we're going to generate some data, and on it we're going to manipulate the data so that way as a machine learning experiment. Originally I was going to use real life data points, but found it just to be a little bit too difficult, and using this toy example we can have a little bit more fun with it than trying to do real predictive analysis on real stuff. You can do that as your projects, but for learning this goal, using goals in a generated data set will be much easier. So the idea here is that God rolls through the Poisson distribution a boldness and intelligence attribute. Oh, a side note is that this may be your first time using Jupyter. Jupyter's fantastic. you can have these it's separated by a bunch of cells, and each cell can be markdown or code. So you just kind of click on it, then you use these hashtags to make titles. The more hashtags, the smaller the text, and these dashes to make lists. You hit Control Enter, and then it will like format it using Markdown. So there's two, and then you just select up here whether you want Markdown or code. See, this won't run as code because it's not Python, it's just Markdown syntax. So then over here, this is a code section. So when I run this, it imports the plotting library and NumPy and pandas. And even here is just I link a bunch of images that I've uploaded to this directory here. And so I'm displaying these images using Markdown. Along with that, you can use LaTeX and put in whole numerical expressions into this type of like this. I can make a little matrix, so 1 2 3, or 1 2 3 3 2 2 1. Yeah, just like that, you can get little matrices. I forgot. I think oh, I forgot the closing. There you go. So you can do all sorts of LaTeX symbolic notation using this. Anyways, back to the goal attributes. So boldness and intelligence is defined by the Poisson distribution. If you don't know what that is, it's very similar to essentially it's the how do I describe the Poisson distribution? It's a discrete probability distribution. It was originally by the guy named Poisson, who was trying to figure out the probability of a cannon hitting the same location twice. So if you're sitting on the side of a street and for 1 minute you count the number of cars that pass by and it's maybe 3, then on average 3 cars will pass by in a minute, and you can use that to figure out the probability of 10 cars passing by in a minute or 1 car passing by in a minute. It makes so the average number of cars passing by per minute would be this lambda right here, and it takes on this form. As lambda approaches infinity, this converges towards the normal distribution. So we use the Poisson distribution because I just wanted to create some sort of value for boldness and intelligence that's just positive. I could have used a percentage, but I thought this would be more fun. So boldness and intelligence is drawn as a random variable, and then timidness is a function of boldness, where essentially the average number of boldness is 100. So 100 divided by boldness is essentially like the ratio above or below the average amount of boldness. So the more bold someone is, the smaller this ratio is. The less bold someone is, the higher this ratio, which makes timid have a negative or inverse relationship, more specifically inverse relationship with boldness, which kind of makes sense. They're kind of antonyms to each other. So then I thought that, being timid might help you get sandwiches, if you're like a bird trying to obtain things. So I gave boldness, intelligence, and timidness a convex combination in order to get the wealth attribute. So theta 1, theta 2, and theta 3 all add up to 0, or all add up to 1, and they represent they represent a percentage of boldness and intelligence and timidness that would result in the amount of wealth. So every time I run this cell right here, it generates a different proportion that boldness, intelligence, and timidness is valued for wealth. It's completely random, but they all are always conserved and add up to 1. So that's what this is. So theta 1 is the weighting for boldness, theta 2 is the weighting for intelligence, theta 3 is the weighting for timidness. So I think it might be helpful to talk about different types of machine learning, like a brief overview. And this book, Hands-on Machine Learning with Scikit, Learn Keras and TensorFlow by O'Reilly is a really good resource. I'll send you guys a link. I don't know. The book's under $50. But right here in the first chapter, it gives a good overview where it goes into types of machine learning. So you have, and this kind of gives a overview of also like why you might want to use machine learning. So there's a supervised and unsupervised learning. Generally, what that means is supervised has some sort of labels in the data set to help the computer learn what it needs to do, whereas unsupervised learning is where you don't have any labels. It's unlabeled data set. Yeah, that's ultimately what it is. So like unsupervised learning could be an example of regressions. It says principal component analysis, linearly localized embedding. I would just say ordinarily squares would be included in that. Then there's all these types of clustering algorithms. Whereas like supervised learning includes if you have a bunch of images and each image has a name to it, like birds versus frogs, and you wanted some sort of classifier, a computer program to be able to classify whether it was a bird or a frog. Great, I figured out how to put my face in here. So the whole point of this was just to create some random variables that have some sort of relationship with them, and ultimately we're going to use machine learning to predict it. And eventually we can give our we want to give our algorithm a boldness, intelligence, and timidness, and predict how much wealth can be obtained from it without giving our program this functional form of timidness or wealth or any of the thetas. So that's the idea. This is not a normal linear regression. This is like a pretty complex relationship that's like non-linear. How do you regress on that and make predictions? So we'll go through that. So this is where I set the other parameters for boldness and intelligence. Up here I say it's 100. Timidness, I use this lambda function. A lambda is just a inline function. So like right here, you use the function definition for timidness, where I say define timidness, insert the parameter bold. I'm going to return a variable where I say 100 times capital bold, the constant up here, which is 100, divided by bold, which is the input variable. So this is the same thing here, where timid is equal to the lambda of the input variable bold, and it just returns this value, which is 100 times the constant right here, bold 100, divided by bold, the input variable. So that's so lambdas are inline or anonymous or like functions. They're just functions. Okay. Then down here, I define the wealth lambda, which is the same thing. I input a bold, a smart, a timid variable, and I do 100 times theta 1, theta 2, and theta 3 for each of the respective variables, which is defined right here. It's the same thing. So scroll down a little bit. Now this is me just trying to illustrate what these transformations are, because you guys might be new. Some of you might be new to packages like NumPy and Matplotlib. So here we go. Right here, I say bolds. So that I use bold, smart, timid, and wealth as the variable names in Python, and I just make it plural to represent that it's a list. So I use np.random passant, and I use bold, which is 100 for the average. If you look right here, the parameter for the passant distribution is just this one positive real number, which represents the average, or It's the expectation of the Poisson distribution. So, and then the variance is also going to be that value. So, so I give it 100 and I generate 10,000 samples. Note in Python you can use this underscore, so I can say 10,000, or I can delimitate it using the order of magnitude using an underscore. Essentially, it just will remove underscores in numbers and it's fine. So I do the same thing with smarts. I just generate a whole big list of it. So if I just print bolds, it's just a list of numbers. If I look at the length of it, it's 10,000. If I say what is the type of bolds, it will say it's a numpy array. Yeah, so okay. So I generate two big lists of Poisson distributions. They're essentially equivalent in length, and they also have the same average. So they're very similar, but they're two separate lists because we're going to merge them later into a data frame. This is a short function that I use just to get the range of this list. So it gets the largest value in the data I give it, and it gets the smallest value in the data I give it, and just rounds it to an integer. I use this down here for plotting. It's kind of, maybe it will come up. So right here, this line, I say, I make a figure where, here, if I comment out the bottom part of this, so you'll see okay. Well, so this generates a figure with a width of 12 units and a height of 6 units. I'm not really sure what those mean, but that's generally pretty big. So then the first plot, I make these like subplots. So this is saying I want I want two horizontal plots, and this is the first one. Okay, so if you want to look more about this, you should look up the documentation for it. So it's right here. So the number of rows, the number of columns, and then the index of your subplot. If I run this, it's generating two lists and then it plots them. So right here I have two vertical plots, and then if I do 1, 2, 1, 2, it'll make two horizontal plots. And I think that this is just a little bit too tall, so I'll reduce the height to 3. And there you go. These nice short plots. So this first one is the bold score. It's just plotting a histogram of this Poisson distribution created. And the second, so this is the bold scores and this is the smart scores. You see they're both averaged at 100, and they look pretty much normal, but they're not the Poisson distribution. So then down here, I take the bolds and I run it through the timid lambda. And then I take bold, smarts, and timids, which is just generated here, and I run it through the wealth transformation. So remember, these are defined right here, and I think this is a really interesting thing with Python is that you can create this list of bolds through this Poisson distribution right here, and you can just pass it straight into this lambda, and in which case it will scale it by 100 and then scale it by the inverse of the bold value. So, and then right here we get another transformation where essentially it will multiply the different weights we have for each of these and through the convex combination and then multiply by 100. So it's very easy to transform numpy lists using Python. You just pass it into a function. As long as you're using Python primitives, it won't have any issues with outputting a new list of a similar just transformed. So so the same thing here is that I'm going to make these two subplots showing the histograms of them. And you see they're all at about 100. So all of these attributes given to these goals are centered at 100, but they have an intricate relationship. So Someone with high boldness will have a low timidness. And then the combination of these will result in some sort of wealth averaged at about 100 for all of the goals. Okay, so now let's go into some programming live. So I have all these 4 variables, so let me just create this a data frame with all of these variables in them. So I can just say bolds, or I can pass it just an array of bolds. What else was it? Yeah, bolds, smarts, timids, and wealths. Yeah, okay. So, and then I'm pretty sure I remember how to the constructor for this, but I'm just gonna don't ever be afraid to look stuff up. So I'm just gonna go to numpy data frame just to find the documentation on creating it. So I can say data type and I can set it to whatever data type I want. Really, I want, oh, this is the wrong function, my bad. I want the constructor. Sorry, my space key is broken. Here we go. Great. So, index. So the data frame has an index column. I don't want to have an index column, but here I want to name the columns, column labels. Okay, so it's exactly what I want. So the labels are going to be in order. So boldness, smartness, timidness, and wealth. Okay. Put that right here. So PD is pandas.dataframe. I give it the variables and I give it the columns. Okay, run it. And so we get an error. 4 columns passed. 4 columns passed. Past data had 10,000 columns. Oh, so 1, 2, 3, 4. Let's see. Let's look back at the constructor for a moment. Data, iterable, or a dictionary. Okay, so I know I can actually do this instead. I can also give it a dictionary data object. So bold is bolds, smart is smarts, timid is timids, and wealth is wealths. Okay, is that right? Yes, that's right. Okay, cool. So then it might just pick up the labels then. Print goals. Great. So yeah, it looks like wealth is actually, oh, here we go. So timids, wealths. Okay, so timid score is actually, yeah, it looks quite different, and wealth score is around 100,000. Okay. So now we got all that. So now we can choose one of our many Scikit machine learning algorithms we can just decide one to make a prediction. I think that we should start with the random forest. So Scikit random forest. So the way that the random forest works is it uses this thing called a decision tree. And a decision tree is essentially a bunch of if statements used to minimize some sort of metric of error on the data set. So you can see here on this lighter line, it's almost like overfit with if statements to the point where like it will say if it's at exactly this x point, then the y should be exactly this point. So your decision tree can, and by overfit, the data is a term used in machine learning to refer to the fact that like your algorithm is so representative of the specific data set you use to train it that it is not generalizable. It only knows how to perfectly predict the data set you've used to train your data, and given a new data point, it has absolutely no idea what to do with it. It's overfit on the original data set. So I can go into decision trees later, but I just want to implement this random forest. Oh, so a random forest is an orchestra of decision trees. So you have a bunch of decision trees trained separately, and then you use all their decisions and you kind of aggregate it in a way to create a random forest. So here, I'm gonna do a decision tree, and then I'll show you guys immediately how we'll compare it to the random forest, which is an ensemble, which just means it's a collection of decision trees. I won't go into the details of like why a random forest would be better. Yeah, but so again, I always recommend just like looking at the documentation for stuff. So this is the Scikit documentation website. You can just search interesting decision tree Python Scikit, and it will just be the first result right here. So yeah, so this is a super straightforward data set where I can just get this the classifier. I can either get a classifier or regressor. So the classifier would be able to distinguish between maybe a bold versus a timid goal, versus a regressor, I think is what we're going to go for, because there's a continuum of bold and timid goals. We want to be able to predict the wealth of a goal based on the bold, smart, and timid aspects of the goal. So yeah, so we can just go through this documentation. So CLF fit, so we can just create the tree. I'll just say tree. Is a decision tree classifier. Okay, so then we can go like this. The next one would be tree, and we're given our data frame here. I can separate it out though, but I'll just go Gulls, tree.fit, goals, and then I'll just give it bold, smart, and timid, and I want it to predict goals, wealth. There you go. Here. Okay, so I just quickly need to figure out the right syntax for this. I think it's, I would pass it. So what I'm trying to do is subset the, okay, so let me just show you the data frame right now. Just do Gulls. We have columns bold, smart, and timid, and wealth. And what I want to do is, if I give the bracketed syntax and just go bold, it will just give me the bold column. But I want also the smart and timid column. So I think what I do is so see here, I just put them as a list. I think I'm supposed to pass it an array like this. Yeah, and there we go. So this is my X, and put it like this. My Y is going to be Gulls, wealth. Okay, so then just put X, y. Continuous. The label is continuous. Print x through 100 rows. Print y. The label is continuous. Oh, because the wealth is a continuous variable. So let's look at this for a moment. So, y is an array of integer values. Oh, because I'm doing classifier. So I actually want a regressor. So the classifier would mean that the output variable should be categories, but I'm not doing categories, I'm doing a continuum, so I'll do regressor. So, okay. I think it's important to kind of watch my mistakes, so that we can kind of see how I also debug something when something happens that I don't expect. So regressions. So I just fit the data, and here we go. So it's done. So tree is now my regressors. I gave it the default width. So here, if we go to the documentation, we see default is best. The strategy used to split each node. Max depth is none. So it'll kind of overfit the data, but that's okay. Okay, so now we can say given, my apologies. What you're supposed to generally do is create a training set, a test set, and a validation set. So I didn't do that, but it's okay because we generate the data. So this data set was created very easily using these 4 lines. So down here, I'm going to say def generate data. Okay, and I'll just give it n is equal to 1000. Okay. And all we do is create bolds, smarts, okay, timids, and wealths. Okay. And then we return the, we can just copy all this and reuse it. So create this data set and then return PDF data frame data set. Sorry if I'm not explaining enough, but essentially now this function can generate data sets. So we just fit this based on 10,000. So now I'll make a test set. So test set of generate data, and let's do 100. Okay. Great. So now I can. The way I can do this is so test. I want to see the test set. Test set. Okay. So we have these values. So, or actually, let's just do 10. 10 for now. Why is it go 10,000 rows? Oh. So, sorry. So, there we go. Okay, so we just got 10 values right here. So now I can do tree dot, oops, lowercase, tree dot predict given the test set. So now I can do bold, smart, timid. Okay. It will predict the wealth. Predicted wealth. Okay. So we use this decision tree that we just trained here based on the 10,000 data points we originally did. So we just trained this decision tree on these 10,000 points, we just created a function to just generate more data, because that's kind of the benefit of doing this like goal model instead of doing real world data, is that like we just need more data, we just generate more data. So to better show the utility of machine learning, and then in your projects you can apply it to real world data and find out how hard it is, how the crux of machine learning is really just collecting good data. So then we generated 10 more data points based on the thetas and parameters that have already been set. And then finally, we used the model we already trained called tree, and we predicted it based on the 10 values given here. So the moment of truth is now we're going to take these predicted values, which should line up with this column here. So so I'll just do test set wealth, and so this is the column of values that we hope the model has predicted, and this is the actual data set that the model has predicted. So I'm just going to quickly put this into a data frame, so pd.dataframe, so that way it's just in a column, and we'll do column so there you go. And then so, and look at that, really precise. Like, so I hope you understand, like this is the actual data, this is predicted values, okay, and this is spot on to an extreme decimal. So this all occurred because our training data set was so large. So here, let's go all the way up. Actually, I'm going to take this. I kind of like the way we set it up iteratively, but over here in the parameters, I'm going to do this, say training size, and instead of setting it to 10,000, I'm going to set it to 100. And the idea here is by reducing this, we're gonna not get as precise data. So I'm just gonna, or here, all right, let's just leave that the way it. Wait, no, let's do it. So I'm gonna reset the kernel, and then I'll show you guys how to make a different plot that will be more intuitive. So reset the kernel, and all variables we lost, and I'll start from the beginning. So it's running through each one now. See, now it's not a perfect normal distribution anymore. So labels is not defined. That's because we just wanted to do the data set. Okay. And go through, print the goals, still 100 data points, sklearn, get the tree regressor, this stuff. So now we have 100 more data points. Okay, now we're gonna fit the data on just 100 data points. Okay. Now we're just gonna generate 10 more data points, okay? And we're gonna make a prediction, take out the wealth, and we're gonna make another prediction. Okay. And now you see it's still pretty good. It's still pretty good, but now it's off. By a significant value. Okay, so I think there's and let's do this now. Okay, so for I in range, and let's run 100. Okay, each time we'll, so we're training size is equal to I times 100. I times so 10 to the power of, let's see, I want it to go up a lot to max 10,000, so I'll just do I times 100. Yeah, sure. This one was really accurate though, so I kind of want to, let's see, I just want to iterate slowly, so let's do I times 10. I want to do steps of 100 starting at 10. Okay. Okay. Then we do training set is equal to training data, training size. Okay. So tree.fit, training set, training on bold, smart, and timid. Remember, bold and smart, just completely random variables, and timid is a product of it, and then wealth is a function of these three. So we do tree so our tree is a decision tree. Okay, and then we do tree dot predict predict using so the training set is this much. Okay, so then test set generate data 10. Oh wait, so training set fit this, fit bold, smart, and timid on just wealth. Okay, and then we want to predict wealth given bold, smart, and timid in the test set instead of the training set. Okay, so predicted wealth. Okay. Okay, so we have a training size, and it's going to go from, I goes from 0 to 99, so it goes from 10, and then it goes to 110, all the way up to about 1,000 is the training size. And the training set gets generated each time. Test set is always just 10 data points, or honestly, let's just test 100, because that'll give us a better representation on how good our machine learning model is. So then we make a decision tree regressor with the with just like the default variables, and then we fit the data using the training set, and then we make a prediction data based on the test set, predicted wealth, predicted wealth, and then now we want to create like the mean squared error, and I know Scikit has something built in, but I'm just going to use like just magnitudes. So predicted wealth is this much, actual wealth is equal to test set wealth. Okay, so then we do, so these are just vectors of numbers, so we can just say what's the difference between them. Okay, NP to absolute value, or let's just how, so we can take the difference between them and then square it, and then NP to SQRT. So this is just absolute value. So I want to do the mean squared error. So the mean squared error. So I want to take okay. Oh, cool. They already have something built in. That's great. I'll just use this. So import, so from sklearn metrics, import mean squared error, okay. So I just go mean squared error, the true versus the predicted, and will give me a value. Okay, so I'll do error is equal to this, and then up here I will say errors and just make a list of them, and just take every error and append error. Okay. Okay, and then I'll just print the error. Here, let's do this. So on iteration I, the error is, and then we give the error, and then we give it to 4 decimal places. Okay. Perfect. Okay, run that. Let's see, error means squared error is not defined. Right here. That's because I didn't run this. Run this. Great. So yeah, we see the errors going down on 100th iteration. So yeah, and we see a little bit of variation here. So again, so size is this. I want to size is equal to okay, so size is growing linearly, so I can just do plt dot line or plot size error. Okay, so then what this will show is the y-axis will be the error of our decision tree, and then plt dot x label, and that is the size in our training set. Okay. And then plt show. Okay, so sizes. Oh. Okay. And there we go. So let me just do plt.y. Scale is log. Okay. There we go. So this is now the y-axis is logarithmic, but you see as our training set goes from 0 to 10,000, we have our error is just drastically decreasing. So this is just showing that as our training set increases in size, our error decreases to practically nothing, which is fantastic. Okay, now let's compare this to an ensemble. So I'm just going to copy this block right here, okay, and drop this decision tree to a random forest. So the big difference is a random forest is it's going to take longer to run. But what it does is it takes a bunch of decision trees and essentially kind of aggregates them. So it just runs a bunch of decision trees all at once because the way that they, so let's see. So random forest classifier, we're using a regressor. Yeah, so it has different errors. The number of trees in the forest default to 100. That's great. So essentially, now we're going to run 100 decision trees at a time and aggregate them. A random forest is a meta estimator that fits the number of classifying decision trees on various subsamples of the data set and uses averaging to improve the predictive accuracy and control over fitting. The subsample size is controlled with the max samples parameter if bootstrap is true. So always use a random forest regressor over decision tree. There's really no point to use just the decision tree unless you're constrained on computational processing. But other than that, random forest. So nothing's changed, same everything. Only difference is I'm going to just immediately print it at the end. Yeah. Okay, an error in our random forest. Okay. See how long this is taking. But okay, so look at this. Before it's even done, I'll get back to you when I might skip the video a little bit. But right here, we're at iteration 10, and our mean squared errors are around 1,000. If I scroll up here, around 10, our mean squared error is like above 1,000 easily. We're still up here. So we start off with 55,000 mean squared error, and it drops down to about below 1,000, around maybe iteration 20. And with this random forest, we went from 40,000 and just dropped like a rock to below that. And clearly this shows that the random forest takes drastically longer to train. Yeah. But I mean, look at that. So we go below 100 here. 100's right here. At 6,000, we're consistently below 100 mean squared error, whereas 100 mean squared error is practically the floor for the decision tree. So it's just clearly better. It just takes longer to process and everything. So I'm just going to do one more. Where I'm just trying to do the training size to be 10,000. So I'm trying to make it really well defined. So pretty much just decision tree once it's set up like this. So this one had an error of 20. So great, now I can fiddle with it. So tree.predict. Okay, so what if, so now I can give it just 3 parameters and it will predict it. So if I have, it goes bold, smart, and timid. So if I go bold, smart, and timid, the most average bird, where everything's equal, based on these plots, I would think that their wealth would be around 10,000. So that I'm betting that their wealth would be 10,000. Sorry, I was supposed to give an array of arrays, 10,000. That's the wealth of the most average bird. So let's make a really dumb bird, but it's bold and timid. So if it's dumber, it just lost a lot of its potential food. So if I just give it more of everything, more bold, more timid, more smart, more food, more wealth. Not by a lot though. Okay. So now let's take a very bold, very timid, very not smart bird. Not a lot of food. Okay, very bold, very not smart bird. Not a lot of food. So it seems pretty even. This makes me think that the thetas are all equal. So let's go back up and see what thetas were picked. So bold is not worth a lot. Intelligence is worth a lot, and timid is worth 30%. So boldness shouldn't matter that much. So let's just put it at 0. Okay. Put that at 100 and that at 100. So this should get me pretty close to 10,000. Boom. So if I'm bold, it goes down. See, this is the decision tree. It's not continuous. It's a bunch of if statements. So anyways, boldness is here. So it's almost like overtrained at this point. I don't know. Anyways, enough having fun with that. So that is now, that's decision trees. What other regressors could we use? I just want to look for a moment at the scatter plots. So training set. So plt.scatter, the training set of bold versus smart. So these are random. So this is randomly distributed positively, so we should just see like a circle, because they should be not correlated to each other at all. Yeah, so let's do marker is a dot. Oops. Go a little thinner. Let's do opacity is 0.3. I think it's called alpha. There you go. Let's do 0.05. Okay, yeah, uncorrelated, boldness, and smart. Okay, but we do know that boldness and timidness is inversely related to each other. And there we go. So the x-axis is boldness, the y-axis is timid, and you see an inverse relationship. Slope's -1, and it's almost even concave because of the Poisson distribution. Or actually, it's because of the division. Okay, now that's cool. So now let's see the relationship between boldness and wealth or food. Okay. It seems uncorrelated, random. Boldness and food. Okay, so let's do a subplot. So plt.subplot 1, 2, 1. Okay. Let's do plt.figure. Fig size is, so I'm making the figure a little bit bigger so that way we can clearly see it. So when I do this, see it's all like awkwardly into the left. Now I do plt.subplot 1, 2, 2. So now on the right, we're going to compare boldness to intelligence. How do I do that? Or I want to do intelligence to wealth. So look at that. So I think this has to do with the fact that, so, okay. If you're more bold, it doesn't affect your wealth very much, hence the circle. Whereas if you're more intelligent, your food goes up. And I think that's reflected up here by the fact that this, the convex combination percentages, where are they? Here they are. 50% makes intelligence and food 50% correlated. Or not really, but that's, they're more correlated than boldness is. Now let's look at timidness, which is at 30%, perfectly in between. So we should maybe see some sort of shape between these two. Okay, so x-axis should now be timid. Y-axis is wealth. Yeah, we do see a little bit more of like a shaping. It's pretty interesting. All right, well, let's run it one more time from the beginning. I'm gonna skip this decision tree here. That was way too long. Decision tree regressor. No, that's fine. Actually, let's stop printing that. Let's only go to 20. Because, and let's do that to 10. Alright, fuck. 20 is fine. Okay. Rerun everything. Because I want to see new, variables for the convex combination. Okay. Now, boldness and intelligence are equivalent, and timidness doesn't affect it at all. So that's interesting. Let's see how it turns out. Let me put this back up here. Sizes is this. I'm just going to append sizes to. There's more efficient ways of doing that. This is the way that it's been done. There you go. It goes down. Nice. We don't need this anymore. Okay. And then I also want to do. And there you go. Cool, cool, cool. So now I'd expect this, so if I go back up, the convex combination, boldness and intelligence should both like have a smeared shape. Wasting my time on this random forest. Great. Yeah, there you go. Okay, next time I will go over TensorFlow. This is just random forest. There's a bunch of other types of machine learning algorithms. You can ask me about any of them, like SVM. You guys do PCA in class, so I can't cover that right now. Random forests are pretty classic just because of their ease of use, and you can pretty much attach them to anything. They have their limitations, as you saw when I was like slightly changing boldness. It wasn't continuous. It had to hit a critical value in order for a different conditional statement to be met in order for the values to change. So it's like a universal tool that's generally kind of weak. So have a good night, guys.